In this video, we will be talking about force couples and couple moments, as well as centroids, center of gravity, and distributed loads, and how they relate to both 2D and 3D problems. In our last video, we talked about moments produced by forces about certain points, and in this video, we're going to explore the same thing, but it's going to be a little bit different. So let's start with talking about force couples. So if I had two forces and they're the same magnitude but opposite direction, we call those force couples. So same magnitude, opposite direction. And this is what we call our force couples. So if I were to draw an example, if I had this force here and this force here, so since it's pointing in the negative direction, or the direction that's opposite to the first one we established, we would call this negative F. Both are the same magnitude. Now, what if we wanted to measure from a point A here? So what we're going to do for this example, we're going to measure our distance for each one separately. So we'll call this A, and we'll call this distance B. So if we were to do that for our point A, so for this moment at A, we start with our red force first. To get to A, we would have to travel counterclockwise, so then that's a positive direction. So then that's our force times our positive A. And then for our green one, since we'd have to travel clockwise to get to A, that's negative direction. And that's our magnitude of F. So we're just going to use our magnitude because we've already established our direction. And that's times A plus this measurement here, B. Now, if we evaluate this, we can factor out our A, our FA. So this is FA minus FA minus FB. And we see that these two terms are going to cancel here. So then that's just going to leave us with negative FB. So you notice because our A isn't in here, that so distance A had no bearing on our moment. Rather, you only need point B. So only distance B is relevant. So when we're solving for force couples, we only need to consider the distance between the couple. So only consider distance between couple. So because A has no bearing, it doesn't really matter where our forces are acting in our system. It only matters that our distance between them stays consistent. So because A has no bearing, we can treat our couples as a free vector. Where they can be applied to any point, but still have the same impact for our moment. All right, so let's take a look at this example here so I can better illustrate what I am talking about. So we're going to match up our vectors. So we have negative force here, positive force here, which is 200 newtons. We have 150 newtons this way and 150 newtons that way. and we want to find resultant couple moments. So we want to find the distance between our 150, so let's call this D1, and we want to find the distances between our 200 newtons, because we only need the distance between both of them. So for this problem, we will need to break down our vectors into x and y components to make it easier to establish the distance that's between them. So break force into x and y, and then you're going to add them all up. So add the sum of all of them. Okay, so I'm going to erase this, and we're going to focus on our 150 just to start things off. So if I were to draw the x components of each one, and now I want to find the vertical distance between them. So remember we talked about moments in our previous lecture, our previous video for our review. We know that when we have horizontal forces, we want to find the vertical distance between them, and when we have vertical vectors, we want to find the horizontal distance between them. So in this case, we are looking for our vertical distance, which given by the scale over here is 4 meters. So I'm going to draw this out just like that. And this is the x component. So this will be our distance of 4 meters, and our magnitude of our force is 150 cos 30. Okay, next part for our 150 is our vertical components. So vertical components pointing up, and our vertical component pointing down. And now we want to find the horizontal distance between them, and we know that is 4 as well. So let's illustrate that. So then this is 150 sine 30, and this is a distance of 4 meters. Let's illustrate for our 200. So let's find positive y component and a negative y component, and the distance between them is 2 meters. So then now we have our vertical components. And what is this? This is 200, 4 over 5, separated by 2 meters. And then our last one, our x components. So then we have separated by a vertical distance how much is that? That is 4 meters, I believe. Yep, that is 4 meters. So now we're going to want to add each of these values up. Sorry, this is 200, 3 over 5. So we're going to take the sum of all of these. So resultant couple moment. So we know couple moment is force times distance. So we're going to do that for each component here. So our first one, our force is, so this is 1, force is 150 cos 30, and our distance is 4 meters. And if we were to connect, so if we were to get rid of this line in between, if we drew arrows that connected the tips to the tails of each one, we would see that this causes a clockwise rotation. So we're going to put a negative there. Same thing goes for this next one here. That is also clockwise, so that's minus. Then that's 150 sine 30, 4 meters. Next up, we have our 200, and this is in a counterclockwise direction. So this is 200, 4 over 5 times our distance, 2. And this is also a counterclockwise rotation. So then that is positive 200, 3 over 5 times 4 is our separation distance. And so when you add these all together, sorry, I made a mistake. The separation distance is 2. Yep, sorry. That's my bad. So then that gives us negative 259.615 newtons per meter overall. You can also say that's equal to 259.615. And if we want to add direction, we can put that in counterclockwise because it is negative. Okay, so that is our first example solved. So next we're going to talk about this pipe segment. So from our previous video, we know that our moment is equal to the distance, so the position vector, times our force. In this case, our position vector is the separation distance between the two vectors. So that is this point right here. So this represents our R. So that's from the point of application of the first one and to our second one. So because this needs to be a directional vector, not just a distance, in this analysis, let's say it points from our downward 25 to our upward 25. So in this case, use the F direction the position vector ends at. So since our position vector ends at the 25 newtons that points upwards, that means we are going to want to use a positive k direction for that. So if we were to write this out, this would be equal to, so we have 0.6. So this would be your x direction we want. So this is 0.6 cos 30 in our I direction. So that's right here. And we need our k direction, which is negative 0.6 sine 30k. And that is the cross product with our 25 newtons. So that's 25 newtons in our k direction. So let's put this into our system. So this is 0, 0, 25. And negative 0.6 sine 30. This is 0. So then that's going to give us a j component. So if we cover these two up, that's 25 times 0.6. 25 times 0.6 sorry, cos 30. And that's equal to 25 times 0.6 cos 30. It's equal to 12.990 in our j direction. And now if we were to add a direction, so since we started from our downwards to our upwards and we connect them together, that causes a clockwise rotation, right, if we were looking at it from this point on. So then that gives negative 12.990j. Okay, our next question is asking us to replace a system with just one resultant force and one couple moment at point A. So the first part is to find our resultant forces. So let's do that. So this is, let's call this F1. So then F1x is equal to 0. We have no x component. Then F1y is equal to negative 300 newtons because we are going downwards. Let's call this F2. So then F2x is equal to our sine. So that's 90 sine 30. And this would be in the positive x direction. Then our F2y is in our negative direction, and that's 900 cos 30. So let's sum up our x's, which is equal to 900 sine 30. And then our sum of our y is equal to negative 300 minus 900 cos 30. And if we find the resultant, that is equal to, so it's 900 sine 30 squared plus our, I'm just going to write summation of fy squared, and that's going to give us sorry, give me a second. And this gives us, that's a really big number. I'm not sure if I did that right. Let's see. Okay, the answer that I'm getting is let me just see if I'm right. Okay, so those seem to be the right numbers. So this is our resultant force in newtons. Sorry, this was a calculation error on my part. This will be negative 1079.422 newtons as our resultant force. And now to find our moment. So let's find our moment just with each of these components on their own. So we'll start with, point A. So start with this one. So this is 300 times our horizontal distance. So that's 0.75 times 3, 2.25 meters. And we have to go clockwise, so that's negative. And our x component is in line with our a, so we're not going to use the x component of F2. So instead, we're just going to use 900 cos 30, and the distance that it is from there, 0.75 times 2, and that's 1.5 meters. And we are also going in a negative direction, clockwise. And we also want to add this free moment here, which is our 300, and that is going counterclockwise, so that's positive. So if we add this all up, this gives us so this is just 0.75. And this turns into, so let me just recalculate that. So that's minus 900 cos 30 times 0.75 plus 300. which is negative 959.567 newtons per meter. And now if you want to find how far to apply this resultant force, we know that our this is equal to our magnitude times our distance, right? So if we were to do that, we want to find what our value of d is, so we can use negative 959. So this only works for our magnitude, so we're going to change that to positive, equals 1079.422 times our distance. And if we divide that over, divide by 79.422, d is equal to 0.889 meters. And let's find our direction of our force. So in our y direction, we have negative 1079. And in our x direction, we have positive 450. So then we know our angle is going this way in our quadrant 3. So if we want the angle that it makes with our x-axis, this is tan inverse of 450 is equal to 67 degrees. And then we have to add 180 degrees because we're in quadrant 3. So that gives 247 degrees. So if we were to redraw this beam, this would look like, so we've got our moment here. Sorry, our moment's in clockwise direction. And this was 959.567 newtons per meter. And then at our resultant, we found to be 0.89 directed this way. And this is 1079.422 newtons. And this is our angle here. And we can just use 67 in this case if we want our direction. But if we were to measure it from here, from our beam, that would be the full 247 degrees. Okay, so that is that question done. So that brings us to centroids and center of gravity. So what are they? So center of gravity, as the name would suggest, is a center of mass. So it in a shape, if you apply loads to either side, so think of like balancing a pen on your finger, right? The point where the pen is in equilibrium, so it's not leaning to either side, that would represent the center of gravity. So also think of it as a fulcrum of a lever. And centroids are used to describe 3D shapes. So centroids describe 3D shapes. So some basic geometry. If we have a rectangle, our center of gravity is half of our x and at half of our y. If we have a triangle, it happens at 1/3 and 1/3 of our y. And for circles, usually that is given to us, but for half circles, which is going to help us in our next question, in our example question, this is at half of x and at a height of 4y over 3 pi. Sorry, 4r. All right, so keeping that in mind, the method to solve for centroids is simple. So we break out shapes, find position of center of gravity for each shape, find area of each shape, and then we're going to find, so multiply position by area. And then with our sums, we can use our total area to find our center of x, center y, and our center z in this manner. So if we have a 2D system, find our center of x equal to the sum of our areas of x over our total area. To find y, this is our area of y over our total area. And then for 3D systems, we would instead use total volume. So then we would have volume of x over sum of volume. And for our z, that is the sum of our z volume over the sum of volume. So I'll illustrate what all of this means in the next example. So taking a look at this shape right here, let's break it out into different sections. So what I would do, I would start with a rectangle here. Below the x-axis, we have this triangle. We have a semicircle on top, and we have negative area represented as a whole, as a circle. There's 4 different shapes we have to consider. So let's plot these different shapes. So we first start with our rectangle, which has a height of 80. So that means at a height of 40 millimeters, let's convert this to meters. So 0.04 in our y. And for measuring outwards from this x-axis, this is, so that's 120, so half of 120 of our width is 60, so that's 0.06 meters. So that's our first shape. Our next shape is our triangle, which is below our x-axis, so it's going to have negative y coordinate. So then this is 120 divided by 3, which is 40, so that's 0.04 meters. And then that's negative 6 divided by 3, 60 divided by 3, that's 0.02, negative 0.02 meters. And now here's where you have to be careful. Since all of our current shapes are aligned with our x-axis, then we don't have to add anything else. But because our semicircle starts higher, we also have to add our y leading up to it. So this is 80 millimeters, so 0.08 meters, plus, so this is 4r over 3 pi, which is, so our radius is measured to be, let me just clear this up a bit so you can see it. Our radius of our outer circle is 60. So then that's 4 times 0.06 meters over 3 pi, which is equal to, so 4 times 0.06 divided by 3 pi, and that's 0.0254 meters plus that 8, and this is measured to be 0.06 in our x direction. And lastly, we have negative area of our circle. And our center is, so that's 80. .08 meters. That's already given to us. And this is acting at 0.06 meters. So we've separated all of our sections. And now let's create a table to help us organize all of our data. So we're going to need a lot of different things. So we're going to need our component. We need our x of that component, our center of y of that component. Could probably make this closer together. We need an area of each component, and then our area of x and area of y of each component. And I think that's it for now. So this extra space is just going to be for extra work. Okay, so this is total. And this is for 1, 2, 3, 4. So I'm going to keep these color coded. So let's start with our rectangle. Our rectangle has 0.06 for our x and 0.04 for our y. And then if we multiplied and found our area, this is 0.120 times our height, 0.08, and this is 0.0096. And then to find our AX, we multiply our area by our center X for our individual shape. So this is 5.76 times 10 to the negative 4. And then this is 0.096 times 0.04. 3.84 times 10 to the negative 4. Then in blue, so our x was 0.04, our y was negative 0.02, our area is 120, so 0.012, sorry, 0.120 times 0.06 divided by 2 is 0.0036. and we multiply that by 0.04. This is 1.44 times 10 to the negative 4, and negative 0.02 times our 0.0036. This is negative 7.2 times 10 to the negative 5. And now let's take a look at our semicircle. So our semicircle for our y, we had to add 0.08 plus the one that we found on the circle, so that's 0.0254. So that's 0.1054. And this is 0.06. And then to find our area, we take radius, so that's 0.06, that's 60 millimeters squared, times pi, so pi r squared, and then divide that by 2. So then our area is 0.0056, and that's times 0.06, which is 3.3929 times 10 to the negative 4. And then we have 0.1054 times area, and that is 5.96 times 10 to the negative 4. And now for the whole, we need to find negative area. So this is 0.06, 0.08. Our area is negative. So then that's our radius, 0.06 squared. Nope, this is different. 0.04 squared. It's our radius of our inner circle, times pi. And this gives us negative 0.00502 times 0.06. This is negative 3.015 times 10 to the negative 4, 0.08 times our area. And this is negative 4.021 times 10 to the negative 4. And now what we're going to want to do, we want to find the total areas of our shapes. So we don't need these first two columns here. We're going to use the rest of them. So let's start with our total area, plus 0.0036 plus 0.0056 minus 0.00502. And this is 0.01378. Then our AX, so that's 5.76 times 10 to the negative 4, plus 1.44 to the negative 4, plus 3.3929 to the negative 4, and then minus our last one. So this is 7.5779 times 10 to the negative 4. And lastly, for our y, so minus 7.2, negative 5, plus 5.96 to the negative 4, and minus 4.021 to the negative 4. And this is 5.059 times 10 to the negative 4. So now, to find our overall centers, that was AX over our total area. So this becomes, it's divided by 0.01378, 0.03671 meters, which is, so times 1,000, is 36.712 millimeters. That's our first answer. Then to find this, it's our sum of AY over total area. So then that will be 0.0549 meters, which is 54.6 0.992 millimeters. So if we were to find that on our centroid, as a center of gravity on our shape, so that's about here. So it's like a fourth of, actually no, more like a third of our width. And then that's like height, that's about 4. So then that's roughly about here. So our center of gravity would be roughly in that area. Lastly, we're going to be talking about distributed loads. So if we have a beam and we have a distributed load, so that means same magnitude of force being applied in more than one spot evenly, we can replace this with a single force equivalent at a certain distance. So then this would look like just one force in the middle of our whole distributed load. So for rectangular forces, our force is the, distribution times the area it acts, times the length it acts on. And it acts in the center of lengths. So then if this whole length was x, this would be acting at x minus 2. And if we call this w, our magnitude is w times x, still acting in the same direction. Now, if we had a triangular distribution, similar to our centroids, this would also simplify down into one force, which acts at, so if this whole thing was x, this will act at x, a third of x. And for triangular loads, so force is area of triangle. So if I were to write that out, that'd be W2 times x over 2. And it will act at 1/3 length from thicker end. Okay, so that brings us to the end of this notes section. In our next video, we're going to be going through some examples relating to the topics that we just discussed. So I will see you in the next video where we'll be solving some practice questions.